Start, ma'am.
Start.
Yes.
Okay. Good afternoon to all. I'm Dr. Sunita Rani, Department of Mathematics. Today I will discuss about complex numbers. Complex numbers, here there is an expression x plus iota y. We can write complex number x plus iota y. We can express an expression of the form x plus iota y is known as um, a complex number, and it we can denote it as by z, and x and y are here uh, real numbers, and this x is called a real part of the complex number and y is imaginary part of z, and we can write x and y as like this: x is real of z and y is imaginary of z. So we can say that a number of the form x plus iota y is said to be a complex number. There are some basic terms we know very well, and I am repeating here. Iota is, what is iota? Iota square is minus 1. We know very well. Iota square is minus 1, or we can write iota is equal to root minus 1. Similarly, we can find out iota cube, 4, and so on. And from this, we see that iota power 4n is equal to 1. And we see here that the z is equal to x plus iota y is a complex number. We can write this complex number as a ordered pair also. This xy like this in a bracket. This is an ordered pair having same meaning x plus iota y. Or z is a purely imaginary number if a real of z is 0, and complex number is a purely real if imaginary of z is 0. And if there are two complex numbers z1 and z2, then we can say that real of z1 is equal to real of z2 if and only if z1 is equal to z2. Or z1, two complex numbers are equal if and only if their real and imaginary parts are equal. Or in particular, you can say that if z is equal to 0, that means imaginary and real part of the complex number is 0. Next is equality of complex numbers. Two complex numbers z1 and z2 are said to be equal. Uh, Consider two complex number z1 having variables x1 y1, x1 plus iota y1, or second complex number is z2 x2 plus iota y2, or you can write in order pair x2 y2. Both are equal if their corresponding, if their real part is both the real parts are equal and imaginary parts are equal. Uh, Such that x1 is equal to x2 and y1 is equal to y2. Then we can say that two complex numbers are equal. There are some fundamental laws for addition and multiplication of a complex number. If we have two complex numbers, z1 and z2, like here, z1 x1 y1 and z2 x2 y2, there are two complex numbers. We can add the two complex numbers here. See here, first complex number x1 y1 plus x2 y2. After adding, we get corresponding elements x1 plus x2, y1 plus y2, like this. This is the addition of two complex numbers. We can multiply the two numbers also. See here, x1 y1 dot y x2 y2. We can write these at x1 plus iota y1 dot x2 plus iota y2, and after multiplication we get first uh, there are four terms, and after arranging the terms, a real and imaginary part, we get real part is x1 x2 minus y1 y2, and iota terms is x1 y2 plus x2 y1. After simplification of this dot product, we get this result. Next, there are some laws for more than two complex numbers. If there are more than two complex numbers, there are some, and some basic laws, commutative law, associative law, commutative law for multiplication, associative law for multiplication, and distributive law where addition and multiplication both are operations are there. What is commutative law for addition? If there are two complex number and we add like Z1 plus Z2 or Z2 plus Z1, we get the same result. This is commutative law of addition. There is no effect on the addition. However, in any order we can add it. Si- Similar lines, the associative law of addition. If there are three complex numbers Z1, Z2, Z3, first add last two complex numbers and then add with one, or first add first two complex numbers then add with third, we get the same result. No change in the result, both are same. Next is commutative law of multiplication. That means Z1 dot Z2 is equal to Z2 dot Z1. We can multiply the complex number in any order. Associative law of multiplication. Similarly, if there are three complex numbers Z1, Z2, Z3, we can multiply the complex number in any order. First multiply last two complex numbers, then first two complex numbers, after the third, we get the same result. Distributive law of multiplication, there are two operations, plus and dot. Add the two matrices, multiply with first. We get Z1, Z2 plus Z1, Z3. First with second, first with third. This is distributive law of multiplication. Okay, next is additive identity. Additive identity means the identity when we add with the matrix, we get the same matrix. Means you have a matrix xy, x plus eta y, and we add with zero matrix, we get xy again. So look here, xy plus 0, 0, 0, 0 means zero matrix, zero complex number, 0 plus iota 0. You can write as 0 plus iota 0. This is x plus iota y plus 0 plus iota 0. X plus 0, second element is y plus 0. Again, we get xy. That means we can say that 0, 0 is the additive identity of a complex number. Next is additive inverse. Means matrix with their inverse, we get zero matrix. Like xy is a complex number with their negative of the complex number, we get zero complex number. Yes, zero or null complex number is here. Means if you have a complex number x plus iota y and their inverse minus x minus iota y, and after adding this we get 0 plus iota 0. So same here, xy is a matrix, plus minus x minus y is inverse of that matrix, and we after adding that we get 0 0 complex number, 0 plus iota 0. Similarly, there is additive identity, then multiplicative identity. We have a complex number xy, and multiplicative identity, if we multiply any number with a complex number and we get the same complex number. If we multiply by 1 0 means x plus iota 0, we get xy itself. Xy multiply 1 0, we get x plus iota y multiply 1 plus iota 0, and after multiplication we get real part is x dot 1 minus y dot 0, and imaginary with the iota term x dot 0 plus y dot 1. So here this term is 0, this term is 0 means x comma y. We get xy, the matrix itself. We can say that 1 0 is the multiplicative identity for the complex number. Next is multiplicative inverse. If you have a complex number, then you have a multiplicative inverse also. Means we multiply a complex number with their inverse, we get a unit 1. So xy is a complex number. Their Inverse is x dash y dash. Choose x dash y dash is inverse of complex number xy. And x dot x dash x dot x plus iota y dot x dash plus iota y dash is equal to 1 plus iota 0. It should be this, and we have to find out this inverse. What is the value of x dash y dash? First, multiply these terms. After multiplication we get x plus iota y dot x dash plus iota y dash. After multiplication, real part is x dash minus y dash, and imaginary part is xy dash plus x dash y. This is equal to 1 0. Compare the terms with first term is 1 is equal to 1, and second term here this is equal to 1. We get the two equations, and after solving these equations we get x dash and y dash. These are the inverse of a complex number xy. So x dash is equal to this and this. We can say that this is a complex inverse of a complex number, multiplicative inverse of a complex number. Multiply with the complex number, we get a unit matrix. Next is difference and division of two complex numbers. If we have two complex numbers, Z1 and Z2, Z1, similarly, we take x1 plus iota y1 and x2 plus iota y2. After taking difference, Z1 minus Z2 is equal to, we can write Z1 plus minus Z2 also. X1 y1 minus Z2 is minus x2 minus y2. And after adding this, we get x1 minus x2 and y1 minus y2. And this is the difference of the two complex number. Similarly, we can divide the two complex number also. Z1 by Z2. This is Z1. Z2, 1 by Z2, we can write Z2 inverse. This is equal to Z1 is x1, x2. Z2 minus is x2, y2. Z2 is this x2, y2 minus, means inverse, multiplicative inverse of this. And a multiplicative inverse, we know that we have find out here x by x square plus y square minus y by x square by y square, and we use here there are x2 y2 in place of xy. That means x2 by x2 square plus y2 square minus y2 by x2 square plus y2 square. And take the multiplication of the two matrices, two complex numbers. This is x1 plus iota y1. This is this pura full is 1 x. You can write x2 by x2 square plus y2 square minus iota y2 by x2 square plus y2 square, and taking the product of the two complex numbers. And after taking product, we get the real part like this, and imaginary part is this, provided this term is non-zero. And we can say that division of two complex number is this. Next is modulus and argument of complex numbers. How to calculate the modulus of complex number? If we have a complex number, z is equal to x plus iota y, and if x is equal to r cos theta and y is r sin theta, then root of x square plus y square, root of x square plus y square, this is called modulus of z, or we can write it as mod z. Mod z is equal to root of x square plus y square. And argument is theta. Tangent theta is equal to this y by x, or you can write theta is equal to tangent inverse y by x. This is called argument, or you can write amplitude of z. And in short form, ARG, argument, or AMP, amplitude of z. Next, how to represent the complex number geometrically? There is a figure. We have a complex number z x plus iota y, and we can write as ordered paired xy also. Z is equal to xy. Okay, this is z is a point here. P is a point. This is z, whose coordinates are x and y. X with respect to rectangular axis x dash o x, and y with respect to y o y dash. This is called a real. Um, axis, and this is imaginary axis. Y of y dash is imaginary axis. And z, this is a complex number having point xy. Okay, this is a representation. And what the complex numbers say in this plane, corresponding to that complex number, there exists one and only one point in that complex plane. Or conversely, you can say that for every points uh, in a complex plane, there exists one and only one complex number, like this. To each complex number, there correspond one and only one point in the xy plane, and each point in the plane. In this plane, for each point, there exists only one complex number, z. If this type of plane you have, then such a plane is called a complex plane. Or you can say it as Gaussian plane or Argand plane also. So, this is the geometrical interpretation of a complex number. How to represent a complex number geometrically. Okay. Next is conjugates of two complex number. If we have a complex number x plus iota y, then its conjugate, it represented by x minus iota y. There is a difference of minus sign in the imaginary part. If you have x minus iota y is a complex number, then its conjugate is x plus iota y. And conjugate of any complex number, we have a complex number z, the conjugate is denoted by z bar. And hence, if there is a any term with bar, that means this is a conjugate of a complex number. And there are some properties of a uh, some results related to conjugate. If you have a complex number z x plus iota y, then z z bar, you can calculate z z bar. Z is x plus iota y, z bar is x minus iota y. And after multiplication, x square, this is minus iota y xy plus iota y xy cancelled, and last term is minus iota y square y becomes x square plus y square. This is x square plus y square, and we know that mod z is equal to root of x square plus y square. Mod z we have discussed here. This is mod z is equal to root of x square plus y square. That means x square plus y square is equal to mod z square. So we can say that z z bar is equal to mod z square. Similarly, argument of z bar, argument of z bar means x minus iota y. Argument means tangent inverse x plus iota y, y by x, but here x minus iota y, minus y by x. This becomes minus of tangent inverse y by x. Or tangent inverse y by x is argument z minus argument z. We can say that argument of z bar is equal to minus argument of z. Okay. Next is if we have two complex number. First is z1 x1 plus iota y1, z2 x2 plus iota y2, and take the sum of the two complex number and then conjugate of that. What is the result? Taking sum of two complex number x1 plus iota y1 plus x2 plus iota y2, and take conjugate also this one. Next, simplify it, taking real and imaginary part separate, x1 plus x2 plus iota y1 plus y2, this one. Next, this is a conjugate term, that means x plus iota y conjugate is x minus iota y, and this one, this becomes x1 plus x2, conjugate becomes plus 2 minus iota y1 plus y2. After simplification, make a complex numbers x1, combine the term x1 with iota minus y1. Sorry, minus iota y1, and second term x2 minus iota y2. This term is z1 bar, this is z2 bar. So we can say that z1 plus z2 bar is equal to z1 bar plus z2 bar. Conjugate of two complex, sum of two complex number is equal to conjugate of complex numbers Similarly, we can easily find the expressions for this Z1 minus Z2 bar. Similar lines. First, add the two complex number, take conjugate, and Z1 plus Z2, arrange the terms, and we get Z1 bar minus Z2 bar. See, and the same line Z1 dot Z2 you can find out. We get Z1 bar dot Z2 bar. And the division is Z1 by Z2 bar is equal to Z1 bar by Z2 bar. And the last one is Z bar, conjugate of Z. Means first take conjugate of Z, then again conjugate, we get the same complex number. Okay, there are some properties, or you can say some theorems also related to conjugate, some modulus of the terms, mode term. There is a theorem, modulus of two, product of two complex number. This is the product of two complex number, Z1, Z2, and modulus of two complex number is equal to the product of their moduli, Z1, Z2. Or in general, we can write product of n complex number, modulus of product of n complex number. We first take the product of n complex number, then mod, and this is equal to product of their moduli. Separate moduli of the complex number. We can prove it also. Take Z1, Z2 mod square. This is mod Z square. Mod Z square is equal to Z bar. And here Z is Z1, Z2. Z1, Z2 into Z1, Z2 bar. Or you can write Z1, Z2, Z1 bar, Z2 bar. Combine Z1 with Z1 bar, Z2 with Z2 bar. We get Z mod Z1 square, mod Z2 square. And this is mod Z1, mod Z2. And similarly, we can generalize the result also. So we can say that modulus of product of two complex number is equal to the product of their moduli. Next, same result for the complex sum of two complex number. Modulus of sum of two complex numbers. We take here the sum of two complex number, then take modulus. It's always less than equal to sum of their moduli. Next is function of a complex variable. How to define a function of a complex variable? First, consider a domain D in a complex plane and Z is any point in the domain D. Z is a complex variable. Here, Z is a complex variable. Then we can define a complex variable. Consider a variable W, and we can define that W is a complex variable. Be a function of a complex variable. W is a complex variable, and we said W is a function of a complex variable Z. We can write W is equal to Fz when W be a function of Z. If to every value of Z in a domain D, every value of Z in domain D, there exist one or more values of W. We can write W is equal to Fz. For every value of Z, we can get one or more values of W. Then we can say that the complex variable W is a function of the variable Z. Function of the complex variable Z, and we denote it by W is equal to Fz. W is a function of Z. W is a function of Z, and we see here that Z is a complex variable in a domain D, and corresponding to every point of Z in D, we get a set of Fz. And we say that set is a range of that function. Okay, W, we can write W as in terms of U plus iota V. We know that Z is equal to X plus iota Y, and W is equal to Fz, F X plus iota Y. And write W in the form of U plus iota v. Fz is u plus iota v. W is equal to uxy plus iota vxy. U and v are functions of two real variables x and y. And W is a Fz, you can write W is u plus iota v. Next, some definitions, single valued and multi-valued function. W is equal to Fz is a function. And how will you define a single valued and multi-valued function? Uh, when W be a single valued? If for every value of Z in D, like W is equal to Fz, for every value of Z, W has one or only one value, then we can say that function is single valued. W takes only one value for each value of Z in D. We can say the function W is a single valued. Single valued if W takes two or more values for some or all values of Z, then we can say this function is multi-valued. If Z has some or many values, for all the values or some values, W has two or more than values, not a single value. W has more values, different values, then we can say that the function is multi-valued function. Next is limit of a function. How to define, how to find the limit of any function, or how to define a limit. What is the how limit exists? If you have a W is a single valued function defined in some neighborhood of D, uh, some neighborhood of a there is a point Z naught in a domain D. Point Z naught is not include here except the point Z naught. We say that Fz tends to a limit L. We can write Fz minus L less than epsilon for Z minus Z naught less than delta. Or we can write that when Z tends to Z naught, when Z tending to Z naught, we can say that Fz tending to L. L is the limit of the function. Means if you have a case for exist a small positive values epsilon and delta for which Z tending to Z naught, we get Fz tending to L, a limit of the function. Then we can define, we say that Fz tends to a limit L as Z tends to Z naught along any path in a defined region, and positive arbitrary number epsilon greater than 0 you can write, or there exists a positive number delta. Delta is depending upon epsilon. This is the definition you can write, or you can use it also. Next is continuity of a complex number. Of function W of a complex variable Z, similar lines we can write in region D continuous at the point Z, Z naught. But here there is a difference. For positive number epsilon greater than 0, positive number means epsilon greater than 0, there exists delta greater than 0. In the limit, delta depending upon epsilon only, but in a continuity, delta depending on epsilon and Z naught both. Then Fz minus Fz naught less than epsilon whenever mode of Z minus Z naught less than delta. There is a difference only one thing, that delta is depend on epsilon and Z naught both. Then Fz minus Fz naught is less than epsilon. Next is differentiability of a function. How to differentiate a complex variable, function of a complex variable, and what is the definition of that? W is a function defined and one valued, means single valued in a domain D of the complex plane, and then we can say as a differentiable at the point if the function Fz minus Fz naught by Z minus Z naught tends to a unique limit, or you can write unique this function Fz minus Fz naught by Z minus Z naught tends to a unique limit when Z tending to Z naught. This denominator term Z tending to Z naught, we can say that Fz minus Fz naught by Z minus Z naught tending to a limit, say L. Or you can write F dash Z naught, the differentiability है here, then we can differentiate F dash Z naught is equal to limit z tending to z naught. In case z tending to z naught, fz minus fz naught by z minus z naught is equal to f dash naught. There is a unique limit of that function. There is a definition of the differentiability of a complex number. Next is conjugate function. If a function fz, we know that fz is a function and z is x plus eta y, and we write it as u plus eta v, u xy plus eta vxy. W is equal to fz. W is u plus eta v. If a function is analytic in a domain D, then the functions u and v, these functions u and v, two variables in x and y, these are called conjugate functions. These are conjugates of each other. U is conjugate of v is conjugate of u. These are conjugate functions. Okay, there is a Cauchy-Riemann equation also. We have a function fz, u plus iota v, and how to calculate Cauchy-Riemann equation, how to know that this function satisfies Cauchy-Riemann equation. First, uh, there is some expressions for this equation. Ux is equal to vy or uy is equal to minus vx. Both the results should be there. Then we can say that the function having Cauchy-Riemann equation. Ux is equal to vy means derivative of u with respect to x is equal to derivative of v with respect to y. If you have both the variables u and v, then you calculate um, the derivative of with respect to x and derivative with respect to y. If both are equal, then find out derivative of u with respect to y, derivative of v with respect to x. If there is a both are equal and there is a negative sign, means if these results holds, then we can say that the function have satisfy Cauchy-Riemann equations. Or we can write these expressions as this: curly u by curly x is equal to curly v by curly y, and curly u by curly y is equal to minus curly v by curly x. Okay, there is some important theorem depending on this Cauchy-Riemann equation. Necessary condition for a function fz to be analytic at a point z. If there is a function fz u plus iota v, we can say the function is analytic at a point if there exists a derivative ux, uy, vx, vy, and equation, the Cauchy-Riemann equation is satisfied. This is ux, vy, uy is minus vx. Okay, if you have a u and v in the expression, and you have to show that the function is analytic, first show that these expressions satisfy Cauchy-Riemann equations. If you have u and v in the expression, first find out curly u by curly x, curly v by curly y, curly u by curly y, and curly v by curly x, and find the expression. This is जो u and v satisfies both the expressions. That means Cauchy-Riemann equation is satisfied. And after applying this theorem, if Cauchy-Riemann equation is satisfied, that means we can say that the function is analytic. So we can find that the function is analytic by applying Cauchy-Riemann equations. Harmonic functions. Real valued function uxy. This is a uxy. This is real valued function. Function w is equal to fz. This is equal to u plus iota v. U is a real valued and is said to be harmonic. When is harmonic? If there exist second order partial derivatives like curly square u by curly x square, curly square u by curly y square. If there exist both the second order partial derivatives, and after adding these derivatives we get zero, that means del square u is equal to curly square u by curly x square plus curly square u by curly y square, and this is equal to zero. We can say that function is harmonic. Del square u is equal to zero, it is Laplace equation. So we can say that the function is harmonic when the Laplace equation is satisfied. Okay, If there is an example depending on the function u, if the example show that the function is harmonic or limit exists or the function is continuous, some of the example is if u is x cube minus 3x y square, show that this function is harmonic. You have u is equal to x cube minus 3x y square. First find out curly u by curly x. Derivative of u with respect to x. This is 3x square. And with respect to x, we get minus 3y square. Similarly, find the derivative with respect to y, curly u by curly y. There is no y. That means derivative is 0. Minus, it becomes minus 6xy. And mass, and for harmonic, to prove harmonic, take the second order derivative. Take the derivative with respect to x again. We get, with respect to x, there is no x, means this is 0. It becomes 6x. And curly u by curly y, with respect to y, we get minus 6x. And after adding, we get that 6x minus 6x, it will be 0. Similarly, if you have u like this, you can show that the function, real valued function u is a analytic function also. First, you have u only. If you have v also, u and v both, then you can calculate that. There is okay, no example I will discuss. If curly u by curly x is curly v by curly y, if these conditions hold in case of u also, in example only u is there, you can try the examples if there is a v also, and find curly u by curly x, curly v by curly y, and match that Cauchy-Riemann equations are satisfied, then you calculate the function is analytic. So analyticity can be proved by the Cauchy-Riemann equation, and all the things which is necessary for the complex number, I have discussed all these. I think you got some useful things related to the complex number, and in your classes you will study all these in detail. I thank you. Thank you. Have a nice day.